You're listening to Make Me Data Literate from the Australian Data Science Education Institute. I'm your host, Dr. Linda McIver, author of Raising Heretics, Teaching Kids to Change the World. Let's go change your mind about data. Welcome back to another episode of Make Me Data Literate. I'm very excited about this one. I think we're going to roam far and wide, just like the last one, and it's going to be a real cracker. So thank you so much for coming. Welcome, Dr. Kat Ross.
Hi, thank you so much for having me.
I'm really excited. So the starting question, who are you and what do you do?
So, as you said, my name is Dr. Kat Ross. I use she, they pronouns, and I'm an astrophysicist. So, I work for the Australian SKA Regional Centre, and my role is as a support scientist. So, everything I do is to help bring science possibilities to the scientist as we build the biggest, best, most incredible telescope in the world in the history of astronomy. So, it's a big global project building this telescope with levels of data that we've never encountered before. So some of the biggest challenges that we've ever faced in astronomy. And I come from the science perspective of I want to do all the science, I want to hoard all the data, I want to keep everything. And I help to bridge that gap between the scientists like me and the software engineers, the engineers building the telescope, and actually make sure that as much science is possible without completely overblowing the amount of data that we have.
That's awesome. I know with the SKAO, there's like you just can't store it all. It's not
We
physically
can't, and
possible. And
it's a really hard lesson to learn as the astronomer, because even in the last couple of years we've made discoveries in the archives of data from telescopes. So they've
yeah.
just been sitting there for 30 years and we haven't known it's there, and then we make this discovery and we go through the archive and see the history of this object, and now we're just facing a whole new world where we basically take the observations and we have to get as much science as we can from it before we delete it. But we don't know what science we don't know. So how do we know that we got all the science from it? That's why I want to hoard all my data, please.
And that's such a good point. I mean, when you look at things like the story of functional MRIs, where
Mm,
it turned out that the first 15 years of using them, the algorithms were quite broken and reporting false results. And, they actually got brain activity out of a dead salmon. So
mm.
you couldn't go back and edit those because they
No,
only had the results, not the original
exactly.
scans. And so you
Yeah,
worry that you're throwing away the good stuff because you don't know how to
yeah.
detect the
We
good
don't know
stuff
what
yet.
we need to keep. Yeah, it's a really big discussion of how do we keep something that's flexible enough that if we make a discovery later on that we need to do more analysis, we can, but not something that's so flexible that we're just keeping all the raw data, because we physically can't do that. To put it in perspective, some of the estimates for the amount of data that will come through when the entire SKA is online, we're expecting volumes that are comparable to the entire internet every day coming through that telescope. So it's just not feasible to keep that level of data every single day,
But also
sadly.
there's this, oh my God, what's in
That's
there kind
so
of,
much
oh.
data. It's amazing.
Ah, that's fun. So, what did you have to learn to do what you're doing now? Was there anything missing from your formal education?
Oh, definitely. I did a Bachelor of Science with a double major in mathematics and physics. The mathematics was actually accidental, so I always wanted to do the physics, and it was definitely astrophysics. And I love math, so just any extra subject that I had was always filled with maths. So when I graduated with a double major, it was a pleasant surprise. Um, but I definitely learned along the way there were a lot of things that it would have been useful to have studied that in undergrad, but I didn't. So I remember in my first year of undergraduate, I had these extra courses. I'd already taken all the maths that I could, I'd already taken all the physics, and I was like, what else now? And I remember my dad saying, oh, maybe take some sort of coding or software engineering or something like that. And I was like, I'm doing physics. I won't need that. That's such a waste of time. So that was one of the bigger mistakes of my life, to not take any kind of programming. So then all of the programming that I learnt was sort of along the way, doing it on the spot as part of other projects, never actually formally learning to code. And then I got to my honours year, a sort of extra year to latch onto my undergraduate. and I did an entire honors research project on simulations of dust grains around a star, which
Oh, wow.
requires a significant amount of coding.
All
And
coding
I
all the
went from
time.
just, yeah, I went from nothing to thrown into the deep end, simulate these dust grains.
Oh,
And
boy.
yeah, it was certainly one way to learn. Not sure I would recommend it as the best way to learn, but it got the job done. I learned trial by fire. So
What were you simulating in?
I was using MATLAB, and I
Oof.
used MATLAB mainly because it was the only language that I had any knowledge of. It was the only one that we did in undergrad as part of our physics labs. We were doing some stuff in MATLAB, but it was never actually, we were never taught to code in MATLAB. But I
Mm.
honestly didn't even know what else was out there. I don't think I'd even heard
Yep.
of Python.
Yep.
And then I finished, and everyone was like, "Why did you do this in MATLAB?" And I was like, "What else is there? Is there another option?" And I would have had a significantly faster route if I had done something in Python anyway.
That's kind of one of the dirty secrets of science, that a lot of things happen the way they happen only because that's what the researcher knew, or that's what the student supervisor knew, or like
Mm-hmm.
that's what, happened to be the dominant package in the lab that they were working in, or, that sort of,
Absolutely.
it's not necessarily what is the best tool for the job. It's like, what do I have to hand that'll work?
Yeah, you're absolutely right. IDL was actually a language I also used in my honors. And that was because I was simulating these dust grains to match an observation. And the processing of those observations was using a pipeline that was written in IDL. And the only reason it was in IDL was because exactly my supervisor was familiar with it. But IDL you can only get with a private license. It's not really one that you have public access to. So I had no experience with it. I didn't know anything about it. There was also very little support online for it. And half the reason it even still exists is because there are enough pipelines around that rely on IDL, and it's more effort to convert them to a different language than it is to just keep IDL around and let them keep working. So I had also used IDL, and so I came out of my honors just being like, I know how to code in these things, and everyone was like, that's the most unhelpful skill. No one will need this. Yeah, so even when I did learn to code, it wasn't necessarily transferable straight away to the coding that I do now, because yeah, so much of it was just done by default of what was around. Yeah.
Yep. Yep. Did you
Mm.
learn any data skills in the course of your degree?
Not really, not in my degree. I took a course of data science in my honors year, but that was really the first time that I'd done any formal data science stuff.
Mm.
A lot of it was really in my PhD of sort of playing catch up. And thankfully, there's people in my institute, for example, this is a very new emerging field. And I would argue there are some people that still don't think it's actually a field yet because there's just not enough people that do it. But we have like biostatistics of we realize the information we get from biology fields, we need proper statisticians that are also familiar with biology to understand and interpret and create the statistics necessary. And astronomy is kind of rapidly realizing that that's a severe missing part of what we have. So astrostatistics is this sort of ever-growing field. And so I was very lucky that in my institute we have an astrostatistician around who could actually help me interpret a lot of this data. I went from studying and simulating the dust grains around one single star that's actually in the northern hemisphere. So I spent my entire honors monitoring this one star that I'd never actually seen with my own eyes.
Oh, that's
To
me.
then, it was so heartbreaking. People would be like, "Which star is yours?" And I'm like, "I can't even show it to you. It's not here. You can't see it here." So devastating. Um, and then I went from the dust grains around this single star to studying surveys of hundreds of thousands of radio galaxies. So the volume of data changed significantly rather than delving into the itty bitty details of a very specific object. It was you have ginormous populations. How do you draw any kind of conclusions on those populations? And coming from a very little statistics background, very little data science background, being able to turn through that data and actually get meaning from it and interpret things was a brand new skill for me. And once again, trial by fire, I guess, it seems to be a common theme. Learned on the job, figured it out as I went.
That's been the story of, I think, almost everyone I've had on the podcast. Been, oh hell yeah, I had to figure that out on the go, like because I couldn't
I
do it
mean,
otherwise.
exactly. And I had no idea that that's where I was going to be either. I mean, astronomy, yes, there are things that haven't changed for billions of years, but it is also a rapidly changing field in a lot of ways. So
Yeah.
the objects that I study now, the things that I study, and the way that I study them, the telescopes that I use, a lot of them weren't around when I would have been making these decisions. So there's no way for me to predict that. And I think it's in some ways a good thing of like you can't really choose wrong because how would you know? But in some ways it's frustrating because you're like, well, how do I prepare? I can
Yeah.
only ever learn on the job, I guess. But I personally like it because it means I always get to learn something new. And I find it much more interesting to learn this new thing when it's for something interesting. Stats was always really boring, but the moment I'm doing statistics on my little baby black holes, I'm suddenly very interested in figuring out the correct statistics.
That's I mean that's so much the message that I keep hammering in all of my work, which is there is no point in asking kids to learn something that they can't see the point in. You've got to make it real, you've got to make it meaningful, you've got to
I don't care about a
put it
bag full of
something they
red and
care
blue
about.
balls. No,
Oh
so
man,
boring. So boring.
that's yeah, that's my pet peeve. I went through
Mm,
the math methods curriculum recently for the senior secondary, and all of
mhm.
the probability stuff was balls in urns. I'm like, what are you doing?
Yeah.
There are so
And you can
many
do
more
really
interesting things.
interesting probability. Yeah, you can
Yeah,
still teach the same thing, but make it interesting.
yeah,
Or give various options and let the teachers be like, actually, my class is particularly interested in this. We're going to
yeah,
teach the same mathematics, the same statistics, but in this scenario, something
yeah,
that's far more interesting. Yeah,
yeah,
relatable. Mm,
100%.
yes.
Is there one thing that you wish everyone knew about data? One thing where you go, man, if everyone understood this, it would be so much better.
I think, and it's certainly the case, I find particularly in an area like physics, which kind of has this perception of being something that's so rigorous and fundamental, and we're always trying to find this fundamental understanding of the universe. So there is this truth that's there, and we're sifting through the data to find that truth or to understand that truth. I think that's kind of the view that we have of what physics is, and particularly astronomy. You know, it's there are these rules and laws of how things work, and when we take these observations, we're trying to find what that rule and law is that's dictating the motion of these galaxies or these atoms around in the star, whatever it might be. And I think that gives the perception that when we take this data, the story is there and we're using the maths and the data science to sift through and find it. When actually, I think we need to change that view that there are multiple stories intertwining in this data. And it is about understanding how to unravel them as much as you can, but also knowing that anyone can kind of create the story that they want in that data. You can work with the data because you have so many intertwining stories. There isn't this one fundamental truth that you're kind of honing in on. In fact, what you're trying to do is understand the complexity of different narratives, different stories, different truths, and how they interact together to create one final outcome, which is where, when we look at the universe, every single galaxy is unique. They are all their own little snowflake. Everyone is different. But that means when we're trying to draw conclusions of how do galaxies evolve, you're looking at these broad strokes populations, you're looking at these huge volumes of data. For example, as I said, I worked on hundreds of thousands of galaxies and I sifted through the hundreds and thousands, these catalogs of galaxies, to try and start to build an idea of how galaxies would evolve and how they change over what timescales and what their sort of evolutionary stages are. But every galaxy, you change one of the many tens of thousands, if not millions of parameters for that galaxy, and you suddenly get a completely different outcome. So you have to gloss over and pick which of those truths, which of those stories is most relevant to what you're trying to determine. And so as a result, we have this perception that physics is so fundamental, that it is so unbiased, that it is such a fundamental truth, when in actuality, the scientists themselves can put so much of their bias in there, so much of their perception just in how they're analyzing that data and what they're picking out. And I think people have that realization for other areas of science, But because, and this is, I could go into the social concepts behind this and the superiority that is embedded in physics as a result of this over tens of hundreds of years and all of this. But because physics has grown as being this superiority where above everyone fundamental truth, I think there's the view that those other scientists, those other fields of science are, less pure because the scientists can impact the story that they're telling. But the same is very, very much true for physics and for astronomy as well. So I think the data, when you see these results coming out, always, no matter the field, no matter how obvious it may seem, there needs to be that grain of there's some level of scientific input in this. There's some level that a person has done this science. And even if it's not the person, let's say it's machine learning or AI, a person has written the machine learning and the AI that has done this analysis. So no matter how it is done, how it is analyzed, and how you sift through the data, there is human intervention and perception that is embedded in that interpretation.
So people who are listening to this podcast in the order in which it comes out will be going, did she put you up to that? Because it's exactly what Emily Carl said last time in the last episode, which I just edited today. It's like the same ideas that, we all bring our context and our bias and our understanding and our experience to the questions that we ask. And you have this massive data, and it's not like just looking at it and going, oh, there's a truth. There's a truth.
I found
there's
thing.
a truth.
Yes.
It's like you have to ask undeniable. A question. You have to look for stuff. You have to know what to look for. If you just have a big, massive data, there's no knowing whether there's anything worth looking for, and there's no knowing what's worth looking for without having to come up with these questions and figure out what to go looking for.
Exactly. And fundamentally in astronomy, as much as, I'm talking about the petabytes and petabytes of data that we'll be generating daily. So yes, there are volumes of data that are just kind of unfathomable that we're processing. But regardless of the volume of data, no matter how much data we take, how many observations we take, there is always fundamentally going to be gaps in the data we take. We cannot observe every single galaxy from the birth of the galaxy to the death of the galaxy. We are not there that entire time. We're drawing conclusions that are filling those gaps. So the scientific method, the process of science, is trying to infer those gaps and understand that narrative given the data that you have. But because, again, you're trying to search for something that is a fundamental truth, but that is intertwined with so many things, and then you're taking great chunks out of it, so that you've got this unfinished puzzle of something that you're not even sure what the final picture is meant to look like. And then you're trying to say that piece potentially looks like this. And so you're drawing so many conclusions with incomplete data, and you're just trying to argue the case that you can, as best you can as well. And so we do a lot of work to kind of try and mitigate the biases that we have. But I think physics has a long way to go. And in fact, I think we're quite far behind many other areas of science in that we mitigate our biases from things like telescopes, the things that are measurable, but we assume the scientist themselves is completely unbiased, where I think many other areas of science recognize the scientist has a big input here, and it's not, and we need to, account for that, or at least try and mention it where possible. But physics seems to be well behind the curve, that it assumes the scientist is perfect in every way. We would never introduce any kind of bias. No.
We're scientists, we're rational thinkers. There's no
exactly.
emotion
I'm
here.
Purely logical. There is no emotion in this whatsoever. And it's a dangerous perception to hold as well, because I think that, for example, that mentality that scientists are logical and pure and away from thought is where you get things like colonization. This is where we had the kind of justification of serious atrocities across the world, because we need to travel to Australia so we can see the transit of Venus, and therefore I am justified in whatever I do for that means, because logically these are the observations that I need, and whatever the means to get there, that's justified. And so the removing of that emotional side and the perception that the emotion has no input in the science is also a very dangerous route to take as well. I think it's important we always remember that scientists are a part of society, and therefore also have all the biases that society has, even if it seems like the science is so irrelevant to society. So it never is.
That's yeah, that's such an important uh,
Mm,
point to make, and it's one of the issues that I have, quite apart from readability, with the whole passive voice um, removal of the scientist from the writing about the science kind of thing.
mhm.
So you don't say we did a thing or I did a thing. You say a thing was done, because the
Yeah.
scientist is not a part of the thing, and that's not
Science
true. It's never
occurred
been
and
true.
scientists
It
weren't
can't.
here. Yeah.
Yeah.
It's not at all what happened. No.
Yeah.
Well, okay, I will say, the galaxy did evolve whether or not I saw it happen, but it's the how I observed it. Definitely, scientists were involved. How we chose to take those observations, how we process them. Yeah.
Yeah. I like that. I think that's the first time anyone has said that about um in answer to that question, and I think it's absolutely one of the fundamental truths that we kind of try to sneak under the rug and pretend isn't there.
Mm,
That people are involved, and people are emotional and biased and complicated and influenced by
exactly.
all kinds of things, and
But I think that
we tend to
that's
believe what's gone before, which is also
exactly.
potentially dangerous.
Yeah, and I think like that comes from the history of sort of the Institute of Science and where science
Mm.
came from. We when we look at modern academic science today, it came from a very Eurocentric Western model, which that was a fundamental part of, being a man of science, that you were above society, that you were like this
Yeah.
was embedded in how we developed science in the modern world. And it's also where we lost a lot of things like Indigenous science, and we lost the Indigenous ways of doing things and knowledge keeping in that way, because it was fundamentally believed that this approach was far better, was far superior. And so it is at the core of science in a modern world that scientists are independent. And I think it is important to, in some ways, remove yourself, but you also
Yeah.
never can. And also, I mean, I know certainly for a lot of the research that I do, the experiences and the history that I have, me as the scientist, has changed how I approach things and has adapted the ways that I want to do my science. Even some little things like when we're making the final image in astronomy, at least for radio, it's a multi-step process where you kind of create a first pass image and you say there is a little source here, there's something bright there, and you draw little boxes, here are where are my little galaxies, and now do another round and clean the image a little bit further, knowing that these galaxies are here. And we're improving algorithms that can automatically detect, oh, I know that there's a galaxy there or a galaxy there. But I personally, in my PhD, when I was processing, I found it really hard to remember. I mean, I have ADHD, so if that wasn't obvious already, I often get distracted. So if I click go on something to process and run this imaging with an automatic algorithm, I would forget about it, wouldn't come back to doing it. But if I have that interactive cleaning of do a little bit, come back to me, I can constantly engage with the image, and it was far more efficient for me to be involved in that processing. But
Mm.
it also actually meant that there was fainter, softer emission that was quite wasn't these little bright dots, but more these big diffuse structures that are really hard for algorithms to pick up. We've actually not got a good system for detecting that yet.
Mm.
So by me being involved in the cleaning, that cleaning actually turned out as a better scientific result. So the experience of the scientist as well, working on pure efficiency and removing the input of the scientist, can actually reduce the science quality also. So it's a very very difficult thing to be assuming, having this idea that scientists should be removed and all the emotion should be removed. It's not actually necessarily the case in any science.
There's always the need for creativity and insight, and
Mm,
we, for all of our technological advancement, we haven't produced systems that can have insight or be creative yet, regardless
yeah,
of what OpenAI may claim.
yeah, yeah,
It's it's a nice little kind of uh, illustrative example of why we can't just one of the reasons why we can't just replace everybody with AI, because
exactly.
it's not there, doesn't have that
It's not.
capability.
And we've been trying for many years in astronomy to bring up machine learning to do a lot of these things, to
Yeah.
identify the galaxies, to classify the stage, the evolution, the type of galaxy. But there is nothing as efficient as a human brain at pattern recognition, and
Mm.
also the uh, detecting these sorts of structures. And once you have that expertise look on it, it is so fast and quick, and you have such a broad expertise to draw on every time you're looking at these images that machine
Yeah.
learning will just never be able to replicate, no
Yeah.
matter how much more advanced it becomes. Mm.
Yeah, and machine learning is really good at very small, very specific, very discrete tasks.
Mm-hmm.
But so you can get a system that's exceptionally good at detecting, say, lung cancer.
Mm-hmm.
Um, but if there also happens to be another thing that shows up on the scan, the machine learning system will completely ignore that. So,
Yeah,
if it says no, there's no lung cancer here, but the scan also includes part of the thyroid, and there's a very obvious cancer in the thyroid, machine learning is not going to report that. So if you never get a
exactly.
radiologist look at it, then you've missed
Mm-hmm.
something really important.
Exactly. Yeah.
What are the worst data mistakes you've seen?
Oh gosh, there's plenty to draw on, I feel. Um, in astrophysics in particular, I think it's quite common. So let me back up a bit, I guess, first. When so I do a lot of outreach. I do a lot of talks to schools, to general public, and part of the reason I do that is A, because I love talking about space, but B, I think space is one of those things that everyone is excited by. Everyone loves to hear about space. I get to say, I found a black hole that burped 700 years ago, and everyone's like, no further questions. That's amazing. No one sort of questions what you're studying. It's all just like, I love this. Whereas, I think climate scientists and biologists that are saying, like, please keep your cat indoors, and everyone's like, oh,
Yeah,
what would you know, my cat would never. And there's a
yeah,
lot more pushback. So it's one of the great things I like talking about space. As a result, though, there's always a lot of interest in space results, in anything astronomy, anything that we're doing. The media is always excited, general public is excited. Space is just a thing that everyone can kind of get behind as being something that's really cool. So as a result, I think it's really common for astronomers to overstretch what their data can actually say. And they make a lot of claims that you do not have the data to actually make that claim. You could hint that this is a possibility, but it is one of, let's say, a dozen possibilities. And in fact, there are far more likely possibilities than this. And I think one of the examples of this, and I mean, I don't know if I can name and shame, I'll keep them as anonymous. There is a particularly well known, outspoken astronomer who says they found evidence for aliens, of these alien structures, because we saw a rock, a meteoroid, flying through the solar system, and the velocity of that rock, and the trajectory that it had, the path that it had. They claim that that means it's sent from aliens in a different solar system, and that could be an explanation, sure. However, Occam's razor, the simplest answer is probably the right answer. And there are so many simple solutions to that, that there is a lot of space debris out there. There's a lot of meteoroids, and it could, in fact, be easily explained by general trajectory, and being a sort of flying meteoroid. It was a weird shape, sure, but there's a lot of weird shapes in space. It's a
yeah.
big place. There's a lot of things there. So to jump straight from we've found something weird, it must be aliens. We are all so keen for things to be aliens. I would
Yep,
love for anything that I observe to be aliens. That would obviously be amazing, but it's you have to do your due diligence first. And
yep,
if you can explain it with something else, it's probably going to be that.
yeah.
And so I think the want for media attention can often outweigh the science of it's probably not as interesting as we think it is, sadly.
Right.
It's still interesting, but probably not aliens.
Yep.
Yeah.
It's that key tenet of science, really, isn't it? That you have to throw everything you can at your
Mm-hmm.
theory to try to disprove it. You're not,
Mm-hmm.
or you shouldn't be setting out to prove your theory. You should be setting out to
Yeah,
disprove it, and we
exactly.
forget that. We get so excited. We're like, oh, I
Yeah.
want to, I just want to confirm what I think I found. No, you should be trying to trying to prove it
Yeah.
wrong, because if you,
And if
if you've
you
tried your
like if
hardest.
you if you can try your hardest and it withstands all of that, then it's
Yeah,
the continuing theory, absolutely. But
yeah,
it's this science is it's done not just by scientists, the individual who are a part of society, but
yeah,
also science done by scientists at large, whole groups, collaborations. The whole
yeah,
point of this is that you publish your results, you argue them, you see other people pushing back on them, and
yeah,
you ultimately work towards the concluding theory that explains what you see. So
yeah,
it's a very natural part of science for you to present results and immediately have someone publish a paper a week later saying, well, that's wrong. Here's why. And I think that's a really great part of science. I love the gossip. I love seeing the back and forth drama. I often really enjoy it. But B, it is an important step of that, and it's when taken out of context. For example, this alien scientist of, well, everyone says is trying to shut me down for this theory, and it's like, no, this
yeah,
is actually a valid part of science. This
yeah,
discussion is actually really, really an important part of this debate stage where we reach that sort of most likely conclusion. And even then, it's never, we've definitely found aliens, we've definitely explained this thing. It's we have a conclusion that fits the data the best with the information that we currently have. This is the most likely scenario. And it's there are several cases in astronomy where there's been this sort of back and forth. We actually recently had a talk from a student here who's giving a background. Intermediate mass black holes are, they're sort of theorized they should be there, but we've not found a single one. We've been looking for decades to try and find these very specific ranges of how massive these black holes are, and we've just not found any. And in particular, we've not found them in these particular types of clusters of stars. So this student was given the overview saying, I'm looking for these black holes in this particular cluster, and this is my method for doing this. And you may ask, have we already found some? Have there been attempts? And they just go through this back and forth of, in the 60s, someone said they found it. And then 65, someone said, no, you didn't. And then we went back and we did find it. And then, no, we did not find it. And then someone came back saying, no, but this could be it. And then the next person, no, but you didn't find it. And so there's just a dozen back and forth of yes, no, yes, no, which I love seeing that narrative as well. Of we look back at some of the things that we used to believe, and you're like, how do we think that? That was so
yeah.
silly of us. But then, someone will think that about what we're thinking at the moment. So,
That's that openness to, but I could be wrong, and I'm going to examine everything that comes in and go, ah, yeah, that okay. So this shows that I'm definitely wrong, or
yeah,
okay, we're still in with a chance here. This is,
yeah,
doesn't conflict with
absolutely.
the hypothesis that we got going. It's that's really good science, but that
It's
whole
also the
human.
exciting part.
Right?
It's the
Because you've
best
just learned
part.
something. You've just discovered something
Yeah,
new. And
and
what
the
you've discovered might be that you were wrong, but that's like
yeah,
that's good. We need this whole new attitude to being wrong. That
yeah,
finding out that your work is flawed, finding out that there are problems with it, finding out that it's
hmm
outright wrong. That's the
hmm
good stuff. Like that's where we make
exactly.
progress.
One of my favorite parts about my job, and this was a big part of my PhD in particular, I found something. I was studying baby black holes, and we expected, even though they're babies, we call them babies, they're still, babies on astronomical scales. So
Yep.
they're still 30,000 light years across. They're ginormous.
Mm.
So we didn't expect them to change unless you watch them for about 30,000 years, which is obviously much longer than my 3-year PhD. So everyone was sort of like, they won't change. We'll just kind of check up on them a year later and make sure our data processing is fine. And so I was doing that, and then I found actually they were all changing. Everyone was doing crazy things. They were all over the shop. And I presented this just being like, everyone's doing a bunch of different things. And people were like, oh, but they can't do that. And I was like, well, they have. So it's actually not about whether or not they can, because they have. So now it's about explaining this. And so
Yep.
I loved that it's a big part of my job to just, I would have, the plots up, my observations up on my screen. And there would be times where it's like a full hour that I'm just sitting there staring at my screen and just coming up with what could explain what I've seen. Like, what if
Yep.
I change this one thing in that theory? What would that look like here? And could that explain what I see? And that is the best part, where you just get to sit and try and explain something. You get to just wildly speculate and come up with something that could explain this. So when someone comes out with a paper that says, no, everything that you've done is wrong, I completely disagree with you, that theory doesn't make sense anymore. Or even like yourself, I have a theory, I take more
Mm.
observations, And now those observations have completely disproven the thing that I was setting out to prove. And so you get to sit there and now again wildly speculate with new information and come up with something new that can explain this. And I think that's the best part of it. So to sit there being like, no, I'm going to keep believing in this theory and take away the best part of my job just so I can claim that I was right the whole time is so upsetting, and yeah, bad science. So
Yeah.
it's the same argument with Pluto. I think people are so emotionally hurt when astronomers decided to reclassify Pluto as a dwarf planet. But that was a moment where the entire community sat there and was like, not only is Pluto not a planet, we can see how all the planets they fit together, they all act really similar. There's a lot of properties that they hold that are all very consistent. And Pluto doesn't match any one of those sorts of things. It has a lot in common, but it is really the oddball here. And that's fine. You can have an oddball, no worries. But it was the moment where we've gone, it doesn't fit here. But we've discovered a whole new class of objects. There's actually so much more out there. So this reclassification, it wasn't a demotion of it's no longer a planet, it's this other sad thing. It was a recognition of there's actually so much more out there that we accept we don't understand. And we're going to start looking at those things that we don't understand. Let's try and understand what they are. Let's try and get more information. So this moment of emotionally sad that, yeah, Pluto, I've always thought of it as a planet and now it's not. And I have to get used to that. But shifting your focus from, instead of saying, I want more planets, more of these things that I already know about, why would you not want more of a whole new thing that we don't know anything about and we get to learn about? It's just changing your perspective on you're not necessarily wrong. You're learning more things.
Yeah. Yeah. And that's something I try to put into the projects that I write and the teacher training that I do too, is the idea that getting things wrong is great because it means you're learning stuff and you're progressing. In fact, my
Absolutely.
son's driving teacher was amazing. Every time Sol made a mistake, he'd be like, "Ah, that's amazing! Like now you know that thing and you won't do it in the test. That's
Yes.
fantastic!" Like it was
Yeah,
such a good attitude to making mistakes. Like
it is.
fabulous! Now you can get past that one. It was
Yeah.
brilliant.
Because
We don't
also,
do
how
enough of
would you
that.
know to point those things out unless you make the mistake?
Yeah,
Unless the mistake happens, you don't know that it was a mistake necessarily.
yeah,
So it's an important step.
yeah.
I
That's
can't
a
even
really
remember
good
what the question
attitude.
was. I've rambled on a whole different direction of whatever we started out as.
That's actually really normal on this podcast, so we're good. Have you ever seen data deliberately misused? And what do you look for? How do you spot it?
Yeah, absolutely. I think it is also one of the things once you are a scientist and you start to notice the important things, even just in your undergraduate, the things are sort of drilled into you in an undergraduate science degree. It becomes very clear when that's not being done for media things, for example. So some of the biggest things I always look out for, any graph that's being reported in the media, what are on the axes? If there are no units on the axes, I will not take any graph seriously. If there's no
Yeah,
label on the axes, I also won't take it seriously. Having just a histogram and saying this bar is bigger than that bar, if I don't know what the bars are, I don't know. It could be a 2 and a 1.
yeah,
And yeah, the 2 is bigger than the 1, but if it's on a scale out of 100, okay, it's not that big. If it's on a scale out of 3, yeah, okay, I might be a little more concerned. So a scale, having proper units, proper description on your graph is a big thing. And also having references. So this is a big thing of even just having the references there is a good sign that I've taken this data from this study. But then having the knowledge of the difference between a study and just a journal article, something that was published in a paper, that is still a source, yes. But if I can't go myself to read that research to see how did they do this study, did they follow the steps correctly? So I've personally read many research papers that were well outside my area of expertise. And I've not necessarily understood the nuance of, this molecule that they're researching or things like that. But being able to study, knowing a good scientific method and knowing the information that's provided in a research paper to see, do I trust the results that they're saying here? And also, can I trust the claims that they're making? Does it seem like they have sufficient data in that paper to make the claim that they're making? And then going, does that claim match what the media is claiming? So there are a lot of times we see papers where the scientist has done everything correctly, has said, we've done this analysis, the data is of this quality, this standard, it's not a huge population, but from this, potentially, we can draw these conclusions. What we need is these observations to help figure out if that is true. And the media will come saying, this is 100% the way we interpret this. There's no wiggle room. So I think the wiggle room scientists are usually very good at including wiggle room in there. We're very good at saying this is not necessarily the complete truth. This is what best explains what I have. I say often, as we've mentioned, that's not necessarily the case all the time. So I think if you're seeing things in the media where it's saying, just scientists without saying which scientists, where, who, just scientists have shown that this thing does this thing, and it's all very 100% clear cut. That sort of phrasing is already quite of a red flag. But as I said, scientists also often will make these mistakes as well and misuse data. And it's picking and choosing the data to support your claim. As I mentioned sort of right at the beginning, there's no fundamental truth that's buried in data. I think we all want there to be. We all assume that there could be, but I just don't think that's the case. I think data is a representation that combines the observer, the methods to collect it, as well as the things that are actually going on. And there usually are multiple things that are going on. So there's a whole bunch of interweaving factors at play that if you are trying to support your hypothesis and you sift away to only have the data that supports your hypothesis, that is a very, very dangerous thing to do. And it's, I think, very common, particularly for people with certain agendas who want to, A, get funding, or B, promote some ideology that they may have, which is a really scary thing when people are not necessarily as data literate to know that that's being manipulated in that way.
But it's also super easy to fall into that trap accidentally, when you're presenting stuff. In fact, I was presenting a workshop on urban heat islands with a friend who is a scientist, and he said, and so here's the temperature in a rural location on this one day, and here's the temperature at the same time in the city. And he went, so you can see that the temperature in rural areas is always lower than it is in the city. I see you rear back and make a face. And I said to him, did you really just take one day and say, and that shows always? And he
one day, 2 data points.
He may have kind of discreetly given me the finger. But he then was like, that's a really good point. And we should, we have to be careful. And, the kids can see that, even scientists do this. And, we have to watch our language and think about the conclusions that we're drawing and ask those critical questions. So the fact that he took that in his stride and was like, oh, heck, I shouldn't have. Like, whoops, that, but it's so easy to do because you know that, the evidence is really strong, and to fall into this proves trap is just like, I think we crave certainty, and so we want to go,
absolutely.
See, I told you.
And I've certainly found, I found in my experience as well, particularly as you become more specialized in certain areas, but also the further I've gotten in my career, there have been times where you kind of make conclusions, but you don't necessarily have the data or the knowledge of where you got that conclusion from. And that does come because your brain is so great at that pattern recognition. And I think ADHD brains in particular are really great at drawing these conclusions from seemingly irrelevant things to everyone else. And so in those ways, I do think that helps how I approach science. But this has happened on multiple occasions where a paper will come out and it'll be like, we've made this wild connection between this feature of a galaxy and this property. And I sit there and I'm like, I thought we knew that from years and years ago because it was such a default thing that I knew. And so the scientists, when you have this vast knowledge, you have so much niche expertise in such a small area of the universe or the world, and you can draw those conclusions, you can make those connections, but often you don't even necessarily realize that you have made those connections as well.
Yeah.
And it can be good in that you're drawing these conclusions, you're making connections on different things and studying the universe in this new way. But it is a dangerous thing of if you don't necessarily realize that. And sometimes they are really obvious of, yeah, country towns or the outback is always cooler, always hotter. I can't even remember what this person said, but it can be so obvious to you, and it might be true, but unless you have the data to make that claim, it is obviously not necessarily something that you should be banking all of your assumptions on and
Yeah.
your entire model.
Yeah.
If it breaks down that assumption doesn't hold true and then your entire model falls apart, you should definitely make sure that thing is true.
Yeah, it's just that kind of fundamental thing of you're always, new information is always coming in. And
Mm,
so then you check your model against the new information and you're like,
hmm
so this doesn't fit, which means something about my model is wrong, or
hmm
something about the measurement is wrong. How do we, check both of those things?
Yeah,
Because
exactly.
they could both be true. Sometimes you
Mm,
get data that's spurious because um, the telescope wasn't well shielded and someone turned the microwave
yeah.
on. Like it's a
Happens to the
thing.
best of us, happens to the
Yeah,
best of us. And
yeah.
I think it's often described as a rite of passage in radio astronomy. And I certainly did it in my PhD, and I've also done it in my postdoc, uh, of discovering something again, basically. And I did a bit of a video on this recently on TikTok and Instagram. So in my PhD, as I said, I was studying these weirdly changing baby black holes that no one said could change, and then they were. So I developed an observing strategy to try and monitor them and see if they were still doing this and get more information on how they were changing, so we could try and figure out what was causing the changes. So I monitored these same galaxies multiple times throughout the year, in lots of different colors, and getting as much information as I could. And this was where I found a very weird thing in my images. It was something unexpected, and it is that moment of, as a scientist, like, I found something cool. It's the greatest thing in the world. Amazing. I've changed the game. But you have to, as a scientist, be like, this is almost certainly not the cool thing. This is probably something boring. Let's not get excited.
Yeah.
And going through doing your due diligence to make sure that it is not something boring before you make a claim that it's something exciting. And so I spent a long time trying to figure out what this was. And it had popped up in multiple images, even though I was looking at different places. So it was the same coordinates. So it wasn't something like a satellite that was, zooming through. And it was there for that entire observing night. So definitely not something that just popped up. But I looked at catalogs from the past with the same telescope, and there was nothing there. So, I'm doing all of these checks, trying to figure out what it could be, and asking around. I wasn't shy about the fact that, like, I found something. It's surely not that interesting, but I don't know what it is. Let's figure it out.
Hmm.
And it was such a mystery. No one could figure it out until I figured, okay, I don't know what this is. It's something really cool. Obviously, it's this big bright thing that's appeared in my observations. What I'll do is I'll take a note of the observation. I'll finish doing the science I am doing, but I'm going to come back and figure out what this is. And as I went to the observer page with that date of observations, they give you a snapshot of what the sky was like at the moment of that observing, which is when I learned that it was the sun.
Oh no. But it wasn't just you, it was everybody you'd shown it to. Like,
Everyone,
it's
that's it.
so
It's
easy to
so it's
do.
one of the great things about radio astronomy. We can observe during the day, but it
Yeah.
does mean that we often forget that the sun exists and that daytime is relevant because we're just observing. It's fine.
Yeah.
And so I discovered the sun, and then I had to go back to all of the scientists being like, "Well, I figured it out. It isn't exciting as we all thought. It was indeed something that was just boring. But I'm glad we sorted it out. Please don't ask me any further details. Thank you so much." But it's a very big rite of passage because that whole process of everything in you wants to be like, I have just discovered something that's like the brightest thing in the sky that
Yeah.
wasn't here a year ago and now it's
Yeah.
here. This is so exciting. And you want to get on the exciting chain. Like, that's what's so cool. But you
Yeah.
have to sit there and be like, but it's probably something boring. Let me just rule out the boring first.
Yeah.
And so far, 99% of the time, it has been something boring. I've heard just in my institute alone, we've had discovery of the moon, the sun, the galaxy. planes, satellites, well-known galaxies. Yeah, we've done it all.
That's fantastic, and I love that you tell those stories because
Mhm,
the process of science is often thought of and described as really quite linear.
mhm.
You did the experiment, you did the work, you did the analysis, you came up with ta-da, amazing thing, but actually so much of science is a happy accident or an unhappy accident in the case of
Yeah.
those stories,
And I
and
just think
we
it's
forget that.
hard as a scientist when that's the only narrative that you get, because all you
Yeah,
see is that these scientists have gone from start to finish,
right.
knowing the entire route, knowing everything that they were going to do. They knew basically the result they were going to get. They set up observations, they processed those observations, and they did get the result that they wanted to get. Like
Yeah,
we assume that that's what it is. So when you deviate from that in any way, or you make what we would call, a stupid mistake of forgetting the sun exists,
yeah,
that it can be so demoralizing, and particularly for anyone who is already struggling to feel like they fit into that environment. Like I already struggled so much with imposter syndrome and just crippling self-doubt of my worthiness of being in such an institute in such a field, to then make this sort of discovery and have to go back to these world leading experts in radio astronomy and be like, it's the sun. I didn't check the sun. I checked everything else and I forgot about the sun. Can be so hard to be like, they must look at me and be like, what an idiot. How did you forget the sun? But because we talk about these things and we openly mention these, and it's, we all have a good laugh about it.
yeah,
Those moments for the next people of, yeah, oh, I discovered the galactic plane in my
yeah,
observations. It's just that moment of like, oh, that was my son. Like I've had my
yeah,
moment. I discovered the sun.
yeah.
Inevitably it's going to happen. Everyone will have that moment. It even happened to Nobel Prize winning scientists who put out an international telegram to say they found a fancy new transient, something that's popped up in the sky that wasn't there, and it was Mars. And then they had to come
Oh,
back being like,
oh,
just
wow.
kidding, never mind, just don't worry about that one actually.
Pay no
So
attention.
everyone, it happens to all of us.
And
And
when your brain is constantly looking to support the hypothesis that I am
mm,
stupid and I am the only one that could possibly have happened
exactly.
to,
Yeah.
then other people telling those stories is
Yeah.
fundamental. And I
And it's
like
once
that you,
again, your brain would sift through the data to only find the data that it
yes,
needs to back up its hypothesis. Yeah.
yes, confirmation
Yeah.
bias is particularly
Absolutely.
problematic in the case of imposter syndrome. And
Yeah.
that segues nicely into one of your passion projects.
Mm.
I shouldn't describe it as a passion project. In fact, I pulled a friend up on that in reference to my work recently.
I don't think it's
One
a
of your
passion
other
project.
projects that you don't get paid for, probably,
Yes.
Inspire Her. Tell me about that.
Include her.
No, include
Yeah.
her. Sorry.
Yeah, that's okay. I mean, I quite like Inspire Her also. It's not inaccurate. That's still very, very much related. So this was work I was doing. So at the end of my honors, I knew I wanted to do a PhD, and I actually didn't get into the PhD program that I wanted to do. So I was kind
Oh,
of in
snap.
this
Neither did
limbo.
I.
Yeah, I was sort of like, oh my gosh, do I have to rethink my entire life? I've been working towards doing a PhD in astrophysics and then I didn't get in.
Mm,
And it was just a big if for me, but I was approached by someone to work in their group on physics education research. So specifically looking at how we can teach teachers so that they can teach students better, and using methods where students will not only understand the information better, but retain the information for longer also.
mm,
And so that was part of my work. I was helping introduce new curricula in New South Wales for physics for high school students, and trying to develop resources and workshops for teachers to help them with this incoming syllabus. It was actually a male colleague at the time who pointed out that in this new curriculum, in the radioactivity section, there's no
mm,
mention of Marie Curie,
mm.
who coined the term radioactive, 2 Nobel
Yeah,
Prizes in radioactivity,
yeah.
discovered the entire field, absolute pioneer, and she's not mentioned. And I was like, that doesn't quite make sense. So I decided to go through and see, why is she not mentioned? Is it just that like we're not mentioning anyone, or
Mm,
who is mentioned and how are they mentioned? And it was basically where I've learned, once you see it, you can't really unsee it. That this narrative of how we were teaching science was only through the lens of this lone male genius, that it was
Yeah.
discovered by a single man
Yeah.
who was inevitably a white man in
Mhm.
Europe in the Enlightenment
Mhm.
period. And that was just when science was done. That was when all of science was done. And we've actually solved
Yeah.
it all now. There's nothing left. It
Yeah.
was all done in that period, finished. And so
Mhm.
not a single woman was mentioned in the entire physics curriculum, but there were, 20 odd men mentioned like 50 times.
Yeah.
So it was this stark reality of I've been dealing with this crippling self doubt and imposter syndrome because there's no one like me. And I'm already well aware that anyone like me, I've kind of already pushed beyond where people like me generally tend to go. I watched
Mm.
everyone dropping out of my undergraduate degree and it just sort of
Yeah.
dwindled till I got to this point. So now I'm seeing that this narrative is being reinforced. This is what we're teaching our students, that not
Yeah.
just is it not for women. If you're interested in physics, your career ends at high school. And
Mm.
that's it. And if you want to do physics, if you want to do science, you should be a man in Europe. That's where it matters. And so it's just a wildly incorrect narrative and
Mm.
also so damaging to all students, not just women,
Mm.
but all students
Mm.
really suffer from that.
Yep.
So this was really the start of Include Her. And it is also a passion project because I am so passionate about it because it is so closely related to my own personal experience. And this is one of those
Mm.
things where I as the scientist, cannot extract myself exclusively from this data and this work. I am fundamentally a part of where this research started and how we've chosen to do this research. So Include Her is now an international team based in
Oh wow.
Australia, the UK, and America. And we've done a full curriculum review of all science courses in Australia for year 11 and 12 students.
That's
So that's
amazing.
environmental science, biochemistry, and physics. And we looked at who was mentioned and how they were mentioned. Are we only mentioning scientists that are, it's Einstein laws, where you're not really mentioning Einstein the scientist, but something that's named after him? Or are we
Yeah.
saying, look at how Einstein revolutionized physics, in which case
Mm.
you're really looking at the scientists themselves.
Mm.
And we found across Australia, there are 145 scientists that are mentioned. Do you want to take a stab at how many are women?
I think it's gonna hurt.
It's definitely going to hurt. It's just how much will it hurt, really?
10?
Just one.
Oh my god.
Not even in double digits. No, just one. Um,
Oh,
and
that
she's only
hurts.
mentioned in Queensland, Northern Territory, and South Australia. So any
Oh
of the other
wow.
states and territories, too bad. Nothing for you. And it's not even Marie Curie, which most people assume it would be her. It's actually Rosalind Franklin. So if you look at the way that she's mentioned, it's often still in the narrative of a man, i.e., Watson and Crick
Yeah.
stealing her work
Yeah.
and winning the Nobel Prize for it. So it's actually less about her incredible methodology. She developed an
Yeah.
entirely new method for imaging, and
Yeah.
none of that. It's about Watson and Crick winning the Nobel Prize for her work. So Include Her is really, that's where we started, is looking at the curriculum, but we've grown a lot since then. It's about changing the narrative that we all hold about what a scientist is, how
Mm.
science is done.
Mm.
A lot of what we're discussing today is related to that, of this perception that scientists are immune to the emotion that comes into
Yeah.
their research, that we are fundamentally completely unbiased and not emotional in what we're doing. And that's not at all true. It's never been true. So
Yeah.
science will always have that level of bias, will always have that level of emotion because it's done by scientists who are
Yeah.
not free from those biases. So how can we change the perception that science is done by a lone individual having a eureka moment and instead look at
Mm.
the fact that science is done by everyone around us and has always been done for well beyond, the Enlightenment period. We look at some of
Mm.
the oldest scientists and innovators here on this continent, and
Mm.
it's there's not necessarily one way to do science. Science is for everyone. There's different approaches, there's different areas, and we're facing incredibly complex and terrifying issues across the world today.
Yeah.
The way that we are approaching them with this stale idea of science is not going to tackle them. So we
Mm.
need to be teaching science in a way that allows for innovation, that allows for the people to come through with the perspectives that we're fundamentally lacking to address these issues as well.
Yeah.
So we're looking at changing curriculum, but also working on workshops. We're doing, hopefully very soon, a big national rollout of our workshop that we've been developing that really sits there and breaks down the narratives that we hold of various science and scientists, science discoveries, um, and trying to shape a different view of what science is and who can do science as well. That was a
That's
very long, rambly introduction to it,
oh
but
no, I was riveted. That's wonderful. And I can absolutely confirm the issue because not that it needs confirming like it's right in front of you, but also when I wrote a talk called Raising Heretics, which then became the start of my book Raising Heretics. And um I gave the talk in front of my friend Nikki Ringland, and she was like, that was fantastic, but also all of your scientists, all of the heretics were men. Maybe we
mm,
could fix that. And I was like,
mm,
oh my God, I didn't even see it because
yeah,
it's what we always see. So
it's just what you
you
do.
just don't
Yeah,
even see it. And
yeah,
so I actually went out and found a bunch of amazing women who were heretics and put them in the talk, and it just
yeah.
made it so much stronger and so much more relatable.
It's so much more
Um,
interesting.
yeah, but it took someone else to call it out. Like I didn't say
Mm,
it. I'd written it. But
yeah,
if you sit there and say, name five scientists, most people will go, men, 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 men.
yeah, absolutely. And then if you ask for women, they're like,
Mm.
oh, Marie Curie, maybe you'll get Rosalind Franklin, but you're unlikely to get many more than that. It's been an
Yeah.
interesting response that a lot of people have where, I say we're not learning of women in science today. The way that we're teaching science, women are just absolutely excluded from this narrative. And
Mm.
people will come back saying, well, I don't know of any women scientists, therefore they don't exist. And you're like, oh, it's so close to the point. You don't know of any women scientists. That is true.
Yeah.
Could that be because you never learnt of them, and just that
Yeah.
that jump of a different interpretation from the same data, the same results, is just too much, and it's you're so close, it's so
Yeah.
frustrating. But
You
I
nearly get
had the
it.
same.
Nearly.
You nearly get it. You're just this close. I had the same realization. I mean, even in my early work of saying for include her, we should be including women. There are women that are easily includable, if that's a word, into the curriculum that we have.
Yeah.
There's easy spots where you're not even changing the content, and you can
Yeah.
just put the names of women that have done this
We're
work.
already talking
Um,
about their work in a lot of cases.
exactly. It's usually just that it was sort of spontaneous knowledge that came out of nowhere, and no one really did it. But
Yeah.
if you put the names of women next to it, you can increase the representation to like 30% without really trying. But I was doing presentations of this, and I actually had a colleague who I'm very thankful that they took me aside afterwards and they were like, I love this presentation. I thought it was really great. But every example that you gave was actually just a white European woman of the women that you should be including. And I
Yeah.
looked at it and I was like, oh my gosh, absolutely. Like I've just done the exact same thing. And
Mm.
so even though I was there advocating for introducing the change, for giving credit where credit is due. Even
Mm.
I'm, holding these biases
Mm.
because it's still embedded this perception that all science is done in Europe and that is the
Mm.
only science. And
Mm.
I laugh when we get taught things like, the Dark Ages, that science just stopped. Everyone was, dying in Europe, and that was all that we could focus on, and science just didn't exist. But
Yeah.
like that's not true. China was thriving. India was moving along like nothing else. Like it's just
Yeah.
this view that Europe is all that happened. That is the only
Yeah.
history we need. And so we get this perception that yeah, the world just went to a standstill for however long the Dark Ages were, and that's just so incorrect.
Yeah.
And so we're missing all that innovation. We're missing all that science. Those narratives that are also part of the reason why people are intrigued in science and want to study science as well. So it's not just about putting the names of women there, but it's also about changing the narrative of how we think science is done. That it's not done by
Yeah.
an individual, it's
Yeah.
groups together working slowly towards an interpretation that makes sense.
And that storytelling is so important. Like stories are
Absolutely.
how we engage,
Mm-hmm.
how we understand and relate to the world. And we got to get better at telling stories.
Absolutely. Yeah.
This
Mm.
has been so fun. What excites you about data?
Oh my gosh. What excites me about data? I think the puzzle of it, the absolute mystery. Um, I love that it's like you're sitting there and you don't quite know what you're going to find. A lot of observations, even if everything went to plan, and I've processed things with the same pipeline that I've done every time.
Mm.
I'm processing at the moment a sky survey using data that's very familiar, a pipeline that's been, working smoothly for many years now, and I helped develop, and everything's good. But still, if I click go on processing this data, there's always something different in it. There's always something weird that requires looking at it.
Yep.
And so I love just sort of piecing together that what on earth is going on, and because maybe it's the ADHD in me that if I was just doing the same thing over and over, I'm inevitably going to get bored. And just processing data,
Yep.
You say it like that, you're like, oh, I process data, I process thousands and thousands of observations each week. And that just sounds so not interesting. But instead, you look at it, I've created this image of galaxies, and there's like a weird splodge that stripes across the sky. And I'm like, there's no satellites in these observations. So what's happening? And trying to figure it out. And then finding one random little feature that if the telescope is pointing low on the horizon over here on the complete opposite side of the horizon, if a bright source is there, you get a splodge in your image, even though you're not looking there. That's such a niche example that we hadn't come across. And I love being able to find these things. So I think my favorite part about data is that it is completely unpredictable. And that may also be my least favorite part about it, but it is my favorite part also.
That makes perfect sense.
Yeah. It's also my favorite and least favorite thing about coding. My favorite thing is that coding does exactly what you tell it to do, and my least favorite thing is that coding does exactly what you tell it to do.
Yes. That's so relatable. Thank you so much. This has been a fantastic conversation, and I love the way there's like a thread running through. I ask everyone the same questions, but the conversation goes everywhere. But there are threads running through, like the connection to the last episode is so strong. And then there was other stuff you said that was like Sarah Beecroft also kind of talked about. And it's great. It's so good. Thank you so much.
Thank you so much. This is so fun. I always love talking about fun problems, weird things in my data. Great.
Fantastic. If you're enjoying Make Me Data Literate, please like it, share it, and even leave a review. And then head on over to the Australian Data Science Education Institute's website to see how else you can support our work.